Hello, my name is Emily Kehoe, and today I will be talking about supernova neutrino estimation for present and future telescopic surveys. A core collapse supernova is a violent explosion that happens at the end of a star's life. The star must have a mass that is 8 times greater than our own sun. These explosions will emit massive amounts of energy in the form of neutrinos. And although these explosions will produce colossal amounts of neutrinos, only around 20 have ever been detected from a single supernova, SN 1987A. In the near future, better telescopic surveys and more sensitive detectors will be up and running and will hopefully be able to detect more supernova neutrinos. Our objectives for this project were to predict the number of neutrinos that can be detected from present and future telescopic surveys and to determine the best range of time and distance to find neutrinos. So how does a core collapse supernova happen? This process begins when a star starts to fuse heavier and heavier elements inside its core, and eventually the core will try to fuse iron into heavier elements, but will fail and cause the star to begin to collapse in on itself. During this process, an immense amount of neutrinos are produced, and a massive nucleus is formed, which creates a shock wave that expands the core and releases neutrinos. The shock wave will become stagnant soon after and turn into an accretion shock. During this phase, neutrinos will react with protons and neutrons and will create a massive amount of energy. If enough energy is produced, a shock revival will occur and will result in a supernova. For this project, we looked at 2 ongoing surveys, the Assassin and the ZTF. Assassin began as a small project in late 2013 with only 4 telescopes, but today has 21 telescopes spread throughout the world and is able to survey both hemispheres in a single night. The ZTF began in 2017 and is only able to scan the northern sky. However, the survey scans more than 3,750 square degrees per hour. For these surveys, we visualize data in several different ways to gauge the importance of various factors. The first visualization we created was a pie chart that shows what types of supernova these surveys found. And core collapse supernova are classified as types 2, 1b, and 1z. And as you can see, about 1/3 of all supernova detected by Assassin were core collapse, while the ZTF had slightly less than that. We also visualized how many supernova each survey detected every year. While Assassin had surveyed between 50 supernova every year, and the ZTF had around 150 to 250 supernova every year. We also looked at the distance distribution of the supernova from the surveys. This histogram was particularly important because closer supernova will have more detectable neutrinos. And as you can see, these surveys typically find neutrinos within the 40 to 160 megaparsec range. We also looked at a future telescopic survey known as the LSST, which is predicted to be in full operations by 2022. The survey will operate at the Vera C. Rubin Observatory in Chile and will observe the entire sky every 3 nights. Because the survey is not running yet, we had to predict how many supernova the survey will detect. As you can see, the survey will be able to detect tens of thousands of supernova every year from our calculations. This is more than ever before, and this is a huge improvement compared to the current surveys. For the current surveys, neutrinos were estimated for every supernova detected. For these detections, we used an energy range between 16 to 30 MeV at the Hyper-K detector in Japan. As you can see, most of these supernova only produced about 1/100th of an event. We summed the events from each supernova and found that Assassin detected 0.3635 events, while the ZTF detected 0.649 events. And for the LSST, we calculated the number of neutrinos based on our estimation of how many supernova it will detect at certain redshifts. For this calculation, we used a limiting magnitude of 24 because we believed this was the best fitting curve, and we found that LSST had a total of 12.2 events per year. Our neutrino estimations for Assassin and ZTF show promising outcomes because they are much higher than we anticipated. For LSST, our estimation for how many supernovae this survey will detect is not as accurate as we had hoped, and in the future, we plan to improve this calculation, which will lead to better neutrino estimations. In the end, this will lead to finding the best strategy to detect neutrinos.